All right, let's dive into a really cool story from the world of medical physics. It's all about how a fundamental bug, a flaw, really, in how we generate X-rays got cleverly turned into an absolutely essential tool for making medical images clearer and safer. So it all kicks off with a puzzle. I mean, think about it. If you were building a camera or any kind of imaging device, you'd want the light source to be perfectly even, right? Uniform. But in a medical X-ray machine, that's not what happens. The beam is lopsided on purpose. So the big question is, why on earth would we design it that way? Well, the answer is this super clever trick, a brilliant bit of engineering that doctors and radiographers use every single day. They use this uneven beam as a tool to perfectly match the X-ray's power to the different thicknesses of the human body. And the result? Much better diagnosis and, believe it or not, a lower radiation dose for the patient. To see how it works, we've got to look inside the machine. Okay, let's pull back the curtain and peek inside the X-ray tube. If we want to solve the mystery of this lopsided beam, we first have to understand how X-rays are even made. And it's actually a surprisingly straightforward process. It really just boils down to two main parts. First, you've got the cathode. Think of it as the starting gun that fires off a super high-speed beam of electrons. Then you've got the anode. That's the target. It's this metal plate that the electrons slam into. And when that collision happens, bam, a ton of energy is released, and some of that energy shoots out as X-rays. So the process is pretty simple. Electrons are fired, they hit the target, and X-rays are born. But here's where it gets really interesting. It's not just that X-rays are made, but where on the anode they're made, and the path they take to get out. This is where our story takes its crucial turn. Okay, so we need to get two terms straight because they're super important here. First is the actual focal spot. That's the physical patch of metal on the anode where the electrons actually land. But because the anode is tilted at an angle, the beam that projects out towards you, the patient, is called the effective focal spot. And it looks like it's coming from a much smaller point. This little bit of geometry, this difference between the actual and the effective spot, is the root cause of our entire lopsided beam. And that brings us to the star of our show, the Anode Heel Effect. That's the official name for this whole phenomenon. It's the reason our X-ray beam is stronger on one side and weaker on the other. So, here's the bottom line. The X-ray beam is not uniform. The side of the beam that's closer to the cathode is more intense, more powerful, and the side that's closer to the anode is weaker. But why does that happen? Okay. Imagine the X-rays aren't just created on the surface, but a little bit inside of the anode's metal. For the X-rays that are heading out towards the cathode side, it's like they've got an express lane to an open door. They have very little metal to travel through, so they escape easily and come out strong and intense. But for the X-rays heading out toward the anode side, it's a whole different ballgame. Because of that angled target, they have to push their way through a much thicker chunk of the anode itself, and that chunk is literally called the heel. All that extra material acts like a filter, absorbing some of the X-rays and weakening the beam. So the longer journey through the heel means a weaker beam comes out. Simple as that. Now here's the really cool part. This isn't just some random, chaotic bug. It's a predictable law of physics. And because it's predictable, it can be controlled. Radiographers can actually manipulate this intensity difference to get the exact image they need. Let's look at how they fine-tune it. They basically have three main dials they can turn. The first is the actual angle of that anode target. A steeper angle means a different journey for the X-rays. Second is the distance from the X-ray source to the detector. And third is the size of the X-ray field they're using for the picture. And this table just lays it all out perfectly. If you want to increase the heel effect, make that difference between the strong side and the weak side more dramatic, you use a smaller anode angle, you move the machine closer, or you use a larger field size. And if you want to decrease the effect to make the beam more even, you just do the opposite. You see, this level of control is what makes it a precision tool, not just a random flaw. So we've got this lopsided beam that we can control. Now for the payoff. How does this actually get used to help people? This is where the physics gets really, really clever and becomes better medicine. This quote just nails it. The whole idea is to match the beam's intensity to the body's density. You use the powerful, high-intensity part of the beam to punch through the thickest, densest parts of the patient. Let's use a perfect real-world example, a human foot. It's not a uniform block of stuff, is it? You've got thick parts and really thin parts. So how do you possibly get one good, clear picture of the whole thing at once? Right,
Here's the challenge. The ankle is thick bone. It's really dense. It needs a lot of X-ray power to get a clear image, but the toes are thin, much less dense. If you use a beam that's strong enough for the ankle, you'll completely overexpose the toes. They'll just look black. And if you use a beam that's weak enough for the toes, you won't see the ankle at all. You're stuck.
And here is the absolutely elegant solution. The radiographer simply orients the X-ray tube so the strong cathode side of the beam is aimed at the thick ankle, and the weaker anode side of the beam is aimed right at the delicate toes. Just like that, the beam's intensity is perfectly matched to the body's own anatomy.
The result is incredible. You get one single, perfectly exposed image where both the dense ankle and the thin toes are crystal clear. The Anode Heel Effect, that original flaw, has been used to create a diagnostically perfect image.
And this technique gets used all the time for all sorts of things. When imaging the abdomen, the stronger beam goes over the dense pelvis. In mammography, the stronger part of the beam is aimed at the thicker tissue near the chest wall. It's a fundamental principle of modern radiology. So the anode heel effect isn't the only trick up their sleeve. It's actually part of a much bigger philosophy of carefully sculpting and controlling the X-ray beam to get the best possible image quality while keeping the patient dose as low as possible. Another key technique is filtration. This is where they place a thin sheet of material, usually aluminum, right in the path of the X-ray beam. The filter's job is to absorb all the really low-energy X-rays. You see, these soft X-rays are too weak to even make it through the patient to create an image, but they are strong enough to get absorbed by the body, which just adds to the radiation dose. Filtering them out is a pure win for patient safety. And this isn't just a random guess. There are precise regulations for this stuff. For a standard X-ray beam, the total filtration has to be at least the equivalent of 2.5 millimeters of aluminum. This ensures all those useless, low-energy X-rays are removed before they ever reach the patient. It's all about crafting the most useful and safest beam possible. So, what started as a physical bug, a totally uneven beam caused by the simple geometry of an X-ray tube, became an absolutely indispensable tool for medical diagnosis. It's just a perfect example of how deeply understanding the physics of our world lets us build incredible, life-saving technology. It really makes you wonder, doesn't it? What other hidden physical principles are quietly at work all around us, making the marvels of modern medicine possible?